Okay, so we're on to resistance. That's part two. Let me go to part one. And we got to make this very quick because I have a feeling it'll go past 15 minutes. So resistance is, come on, come on. It's a phenomenon, we'll call it that reduces current. So think water in a pipe. Let's say you had, oopsies. Let's say you had a bucket. You had a bucket up top full of water, and you had a pipe. Oh, I should turn this so it's straight. You had a pipe pouring the water onto your head. Alright, and this is you. Resistance is anything in that pipe that will slow down the flow of water. So, if you've ever drank from a straw, if you had someone pinch or clog up half the pipe, put a smaller tip on the end. So if your pipe's normally that big, you put a cap on it that pushes it down to that big. And now this cap provides resistance. Okay, so real quick before we go back to the other side, resistance is measured in what's called ohms, and it's that symbol right there, OHMS. Alright, and now we go back to this. So it reduces current. So our current right now is 4 amps. So 4 coulombs per second. Alright? And if we thin out the wire, or make the road a little bit thinner, traffic has to move a little bit slower because it can't fit. So it goes down to 2 amps. And if we had a really, really, really wide road, I'm skipping something, but whatever, we could fit more electrons through in 1 second, so the current increases. We'll get to that part in a second. So I found this little, it's a little setup that helps us understand, or it just demonstrates what's going on. So I have a basic circuit here. Go away. Basic circuit here. There's my battery. I have a ammeter on this leg. I have a voltmeter that was once over a light bulb, but I moved it. And then I have a resistor. And what my resistor does is it slows down the current. So I'll show you what I mean. I'm going to take out that. I'm going to put a light bulb in, right? I'm going to take out the resistor. No, remove. So I take out the resistor, and now my light bulb lights up. In this situation, if I increase my voltage, my light bulb gets brighter. And when I increase my voltage, or my potential difference, the electrons move faster, so my current increases as well. As you can see on that, my current is 5.12, my voltage is 51 volts. So the electrons are moving very, very quickly. They're all carrying lots of energy, and they're giving it off at the bulb. Now, what I can do is slow down how fast those electrons are moving using a resistor. And all a resistor does is adds a bottleneck. So it just says, slow down everybody. So my resistor slowed down my flow of electrons. They're moving nice and fast, but my current went down to 2.56. Remember, before the resistor was at like, what was it, 5 or 50? So let's mess with the resistance a bit. If I increase my resistance, the current drops a lot. Please note, voltage didn't move too much, but that's because the bulb's there. I'll show you that in a second. And if I decrease my resistance, so almost no resistance, the electrons move very quickly. So let's pause that and set up another. So let's put I want to put some nice numbers here. Let's make this 10 ohms. Alright, so we'll make that 10 ohms, and we'll get it to show. My resistor is 10 ohms. We're going to make this 90 volts. Show value. I said 90. Change voltage. Maybe it doesn't. Oh, it doesn't go up to. Yeah. Well, let's make this. Yeah, I want 90. Make this 90 volts. And what I'm going to do is I'm going to take out the light bulb, I'm just going to connect it up normal. So if you look, you'll see that my resistor is 10 ohms, my battery is 90 volts, and my current on my ammeter says 9 amps. And those numbers kind of all go together. When I times this by this, I get that. Alright, so let's go to the other screen. Alright, so what we find is V equals I times R. We're looking straight at it. My voltage is 90, my amps are 9, my ohms are 10. Voltage equals 9 times 10. Perfect. When we rearrange that equation, our resistance is voltage over current. Nice and easy. Something very simple. Now, if I want it to work out, so let me just, before I say that, let me just make sure that we have everything we need for resistance. State that resistance is PD over current and how a change in PD or resistance affects current. Yes, we did that. What happens if I increase my voltage? These guys move faster. What happens if I mess with resistance? They'll move faster or slower. Okay? Recall R equals V over I. Done. Describe an experiment to determine resistance using voltmeter and ammeter. Getting into that in a second. And this part. Oh, this one's easy. This one's part of the slideshow. So let's go back to this one. Resistance is what slows down or speeds up the current in a wire, so to speak. All right. So if we have a medium thickness wire, a good bit of electrons can move through at once. If I made that wire thinner, less electrons could fit without bumping into something, so the resistance increases. Think about 50 of you trying to walk through a small hallway versus 50 of you trying to walk through a big hallway. Not really going to work. If you have a really wide hallway, lots of you can fit through. Keep your wide jokes to yourself. Okay? So thin wires have a very high resistance because there's just not enough space. The length of the wire has an effect as well. Imagine you're walking through a hallway blindfolded again. The longer the hallway, the better the chance you'll bump into something. Cross-section means thickness. All right? So all of this is people trying to walk through a hallway. Go back and work. In the hallway are random chairs and tables, which are the atoms that are in the metal. If you're blindfolded and you're an electron walking down that hallway, the longer the hallway, the better the chance you'll bump into something. So thin wires, you'll definitely bump into something. There's no space to get around it. And long wires, you'll hit as well. So an example again, there's your wire, and in the middle of your wire are random objects all over the place. And your job is to get from one side to the other blindfolded. The longer that hallway, the better the chance you'll hit something. The thinner that hallway, the better the chance you'll hit something. Also, different metals have different amounts of objects in the middle, or these atoms to collide into. So the material can change your resistance. And the last one, the really obvious one, is heat. If we increase heat, these guys aren't just standing still, now they're moving. So imagine you're running down a hallway blindfolded with tables that are moving. Now you have a really high chance of hitting them. That's how you explain this one, resistance of a wire to its length and its diameter. Now let's get into this experiment before I run out of my 15 minutes. Okay, so let's take a look at the most ghetto setup in the world. What I have is a schematic or a circuit diagram of a battery that's 90 volts. I have an ammeter in series. I have a voltmeter in parallel to this red wire, and then I have a resistor. So what we're going to do is try and find out what is the resistance caused by this wire. Alright, so again, what I just drew I have set up here, and I'm going to throw this random piece of wire in. So when we look, I have a voltage of 90, I have 1.33 amps flowing through the entire circuit, and 50 ohms on this resistor. In a regular circuit, if I added these two together, I should get that value, but right now I'm not, and that's because this piece of wire is providing resistance. So to figure out the resistance of that wire, what I do is I look at the voltage, or the potential difference, across that wire. So let's just move this guy just a little bit closer, just to make sure we're getting a proper reading. Alright, so now I have a current of 1.33 and a voltage of 2.91. Remember, R equals V over I, so I can do a calculation. Just to make sure that I'm right, what I'm going to do is decrease my resistance on my resistor to 25, which I can't seem to get properly, so 25. And when I do that, you'll notice that the current increases a bit, my voltage changes just a little bit, and I can keep working out that I equals V over I. I can keep doing that over and over and over again at different resistances on my variable resistor. So we'll put it to 10 ohms just to see what happens. And every time I do that calculation of R equals V over I should get the same number, and that tells me the resistance of my wire. With those, I can plot a graph of V against I, and the slope, which is V over I, will tell me my resistance. Okay, so that's what this little section means. Describe an experiment to determine resistance using a voltmeter and an ammeter. This, recall and quantitatively, blah, 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 blah. Resistance, length, and inverse proportionality with the cross-section of a wire. What that means is, as I'm going to a slightly different topic now, same topic, but, which one of these is going to have the greatest resistance. So when my cross-section goes up, my resistance goes down. And when my cross-section goes down, so the space, if I was to measure that, it'd be, 3? If I measure this, it'd be 6. So when my cross-section goes down, my resistance goes up. That's what inversely proportional means. It means backwards. All right, so quick review. State that resistance is PD over current. Done. Recall R equals V over I. Done. Describe an experiment. That's this bad boy here. Nope, this guy. That's the experiment. And the schematic would look a little bit like that. Just drawn properly with the I tried, okay? At least I tried. Resistance of a wire to length and diameter. Done, done, done. Cool, let's hope this was under 15.